On this page, we just want to remind ourselves about a concept we learned about and touched on in section 11.1, and now it's back a little bit, which is the convergence of Taylor series. So if you let f have derivatives of all orders on an open interval, I, containing a, so in other words, an interval containing your center, then the Taylor series for f centered at that a converges to f for all x in that interval. So as long as you're within your interval of convergence, that's the open interval here. So that's the interval of convergence. As long as you're in that interval of convergence, then the function, the Taylor series, centered at that value within the center, which is the center of that interval, will converges to that function if and only if the limit as n goes to infinity of your remainders is 0. And we have a formula here for the remainders. So let me remind you, just really quickly, what I talked about in section 11.1, which is the remainder piece. Let me take that away. All right, so I have a Taylor series here, which is actually the example on this page, which is e to the x. So the function is e to the x, which is that kind of yellowy orange function. And then the power series, the Taylor series for it, is that black curve right there. And this is actually true for negative infinity to infinity, but I've let myself go just to 3. So I'm only including 3 terms of my Taylor series. And you can see that the points are really close to each other, especially close to our center. So the center is right here at x equals 0. As I move away from that center, then my values are different between the two curves. And I actually wrote it right in here. So y1, let me do this in the same color. So those would be the orange dots, and then y2 would be the Taylor series. So the orange dots and the black dots. And they have a difference between them, which are these red dots down below. So for example, these two dots are separated from each other by 0.03. These two dots right there are separated by 0.002, which is so small you can barely see it. And then of course the center of the interval, for sure, there's no difference at all. So that's what they're talking about. They're talking about the difference between those two. That's called the remainder. And we can come up with a formula for that remainder, which is what I'm about to do. So let me go back here. So recall that the Taylor series for e to the x is equal to what I just showed you. It's from 0 to infinity of x to the k over k factorial, right? Which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Continuing on. All right, so the remainder, according to this theorem, would be equal to e to the constant, because of course the n plus 1th derivative of e to the something is e to the something. So, I mean, I'll just put it this way. The n plus 1th derivative at some constant c over n plus 1 factorial times, and I've centered this, if you'll notice, I'm just talking about this function, so the center is at x equals 0, right? So really, it's a Maclaurin series, you can tell right there. So it's a Taylor series centered at 0. So it's really x to the n plus 1. But of course, the n plus 1th derivative of e to the x is e to the x, right? So that means that the n plus 1th derivative at some constant c, right? And c has to be basically between wherever your x value is and your center. So, if your center's right here, it's got to be, somewhere between that and whatever x value you're specifically looking at. It would just be e to the c. So this means that Rn at x is equal to e to the c over n plus 1 factorial x to the n plus 1. Now technically this could go negative or positive, because if you have a center here at 0, so here's our center right there at 0, you could go left or you could go right. So just to make things a little bit easier, let's take the absolute value. Because we don't really care, sorry, just a little bit dyslexic. We don't really care whether or not it's negative or positive. What we care about is the size of it, the magnitude of it. So what we're going to do is we're going to use the absolute value of Rn of x. All right, so let's do that. Let's take the limit because they want to show it. Oh, so find the remainder. We did that. Here's the remainder. Right? The remainder is right here. And so then show that that remainder has a limit that's 0. So what that's saying is that once you're in your interval of convergence, that remainder has to go to 0 as n goes to infinity. Let me show you on the graph. What they're talking about is the difference between the curve, the real curve, which is the orange one, and the black curve, which is the Taylor series, has to decrease and shrink as I let, in my case, k go to infinity. As I let the number of terms in my Taylor series increase, right? Look what's happening to my remainders. Look here. I know it seems like they're getting bigger. They're not. Let me bring this over really quickly. They're getting super, super tiny. They're going to 0. Right? The more terms I include, right? If I include infinitely many terms, then that remainder is going to 0. That's what I'm trying to prove. And you can see the remainder curve right here. There it is, right? So it's gotten so tiny that it's not really even showing anything. So let me take it back to like 2. There we go. Now it's showing something interesting, right? So 3. Sorry, 3 was what I was working with. Okay, so there you go. So you can see that difference in that curve, right, creates that remainder. And the reason it wasn't working at 2 was I was doing y1 minus y2 specifically. But again, it's kind of easier if you just do the absolute value because that's what we care about, right? So I did absolute values in here because it's just easier. So I did the ABS of x. So if you don't do that, then it would be the other curve that I had. But nevertheless, you can see that remainder, that difference, will shrink as I let k get larger. Right, see how that red curve is closer to the x-axis? If I let k to go 4, it's even closer. If I let k to go to 5, it's really close, right? That orange curve and that black curve are really close for a very long time. And you can see the remainder term over here, well, the absolute value of the remainder, is going to 0. And that's what we're going to prove. So we want to prove that remainder, as n goes to infinity, of Rn of x, and we're just going to use the absolute value because it's easier, is equal to 0. So we want to prove that. So that would be e to the c. Oh, actually, well, I need an absolute. I'm just going to let it be this. So notice that this is less than or equal to e to the absolute value of x over n plus 1 factorial x to the n plus 1. The reason being because c has to be between a and x, right? C is constant. So 0 is less than c, which is less than x, right? C is between those two. Sorry, just less than. So if c is between them, then if you just use absolute values, then this will always be less than e to the x because c is less than the absolute value of x. That's all. All right, so that way I can use e to the absolute value of x over n plus 1 factorial, absolute value of x to the n plus 1, because I'm taking the absolute value of the whole thing. And then, well, where's the n plus 1s? The n plus 1s are here at n plus 1 and n plus 1. The e to the x has no part of it. So I'm just going to pull the e to the x out. And then it's the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial. But that's 0 because the n plus 1 factorial wins. As n goes to infinity, that n plus 1 factorial will be significantly larger than the x to the n. It's because of this growth rate of sequences. Factorials are always larger than a power function, which is what we have. Actually, it's kind of that power function. Either one. X to the n plus 1, right, is way smaller than a factorial. And that's why this is 0 right here. because of that theorem 10.6, the power function will be significantly less than the factorial function. So we did it. We found the remainder using the theorem up above and using the fact that we know that the nth derivative is just e to the c, pretty basic. We use the fact that c is between 0 and x just to make our lives easier. Took the absolute value, turn it all positive, and then used e to the x here instead of e to the c, because c is just some constant between 0 and x. So the biggest you could make it would be x. And so therefore, that's 0. And since that's 0, then that means the limit of Rn of x is 0. But never lose sight of what we're talking about. What we're saying is that if you have a Taylor series and a function, like e to the x, then as I let my Taylor series go towards infinity, then the remainder part, the error, the difference between the two, the curve and the Taylor series, so the curve is the yellow one, Taylor series is the black one, that remainder is the difference between the two. And as you let your Taylor series get larger and larger for the top value for the series, that remainder gets smaller and smaller and smaller. And you can see it right here in the table.